There you go. So we're going to continue our conversation about vibrations, right? In the first class, in the last class, basically, which was our first class, I talked about the history of theory of vibration, what vibration is, or different types of vibrations, or as a general idea, where do we see vibrations? Now, we're going to start with today. We're going to start with some very simple, an very simple oscillating system, a vibrating system, and we're going to use that system to introduce two important concepts, and we'll take it from there. These two concepts are very important. We're going to deal with them pretty much in every class, I would say, from now till the end of the semester. And that system would be a simple pendulum. Right? I'll start from, if you remember when I was talking about the history of theory of vibration, I said the whole like modern idea of vibrating systems started with the story of Galileo, and when he was sitting in a church looking at the chandeliers swinging, what he realized was that the mass of these chandeliers, how heavy they are, or how strong the wind that is blowing and making these pendulums swing, how heavy that wind is, did not really affect how long does it take for a pendulum to go from one side to another and goes to go back to its original position, as we call that a cycle, right? So if you remember, I tried to show it on this small pendulum here. If I just let it go from one side, the time it takes to go to the other side and come back, this is one cycle. And the time that takes to complete that cycle, we said I'm going to define it officially, but that's a period of oscillation or time period. Now we're going to start looking at that simple pendulum, right? And how can we mathematically define the equation of motion, and from there we'll see what we're supposed to do in mechanical vibrations in this course. We want to find a solution for that equation of motion, right? The equation of motion we could find from dynamics from before, so that's not new. Let me put it here. Let's put simple pendulum. Looking at the pendulum, I'll just draw the pendulum here. If I have this pendulum, let's just some support. Right? It's swinging, so I'm just gonna draw the string and a mass attached to it. I'll call this mass, let's say the mass of this this mass of the pendulum is just m, and the pendulum is away from its equilibrium position theta degrees. The equilibrium position is the position at which the pendulum is standing at the beginning and it's not moving. This is straight line, vertical line is the equilibrium point for this pendulum. It can go away. I can pull it away from the equilibrium position. So that's theta. Now let's draw the free body diagram and kinetic diagram for this. Again, from dynamics, depending on how much you remember of the equation of motion, free body diagram, and kinetic diagram, or if you were calling it the inertial forces diagram. All right, so I'm going to draw the free body diagram here. Let's put free body diagram. I have the mass there. Well, mg is pulling it down, and T is the tension in the string. This goes all the way to, let's call this point O. Call this point O. This is equivalent to kinetic diagram, right? The diagram that we use to represent the components of acceleration. So for this, one way to do it is that I can consider this swinging mass as pretty much a rotating object around a fixed point. And if I do that, though, that would be IO alpha. Right? You can look at it a different way, but the way I look at it is just an object rotating, its rotation around the fixed point, if you remember from dynamics. So all I need to do is just form the equation of motion, right? Form the summation of moments around point O is equal to IO alpha, alpha being the angular acceleration. Stop me whenever you feel like it's confusing. I'm hoping that these are all familiar from dynamics. Now, in dynamics, at least from what I know, we didn't really care about the direction of the motion. But here, or the positive direction that we were taking in so many cases, usually we're getting the exact same equation of motion. But here, I always, now and for the rest of the semester, I always take the direction of the motion as positive. So in this case, I assume that this pendulum is swinging this way. So I take this as positive. So that would be the positive direction. Now, let's see what we get out of this. This, I forgot to put the length of this also we need, that's L. So, if I decompose the forces here, well, obviously this is theta, which means we are gonna have one component of mass here and one component of weight, sorry, here. If this is theta, this would be mg cosine theta, and this would be mg sine theta. That's going to help me to find this MO, summation of moments created around point O by all the forces we have. Well, T is passing through point O, so that doesn't create any moment. Mg cosine theta is passing through point O, so it doesn't create any moment. Only thing left is mg sine theta. And I know the distance from here, from this mass to point O is L, right? That's the length of the string. I'm considering this pendulum as a particle. So that will give me, and it's going to be positive, considering that I took this direction as positive direction. So this becomes mgl sine theta. No other force, as I said, T is passing through point O, mg cosine theta is passing through point O, so we're all good, is equal to IO alpha. Now, depending on how much you remember from dynamics, what was the moment of inertia of mass rotating around a point? Do you remember that? I'll welcome any input. Yeah, too early, huh? So mass, the moment of inertia of a mass around the point was pretty much the multiplication of the mass and the squared of the distance from that mass to that point. So for this mass here, well, I represent that the value of mass with m, so that would be ml squared. And what is alpha? Alpha is the acceleration, right? Angular acceleration. What is angular acceleration? Well, angular acceleration is nothing but second derivative of angular displacement with respect to time. What was alpha? Alpha was d squared theta dt2. Second derivative of theta, which is the angular displacement with respect to time. It's just acceleration. And I'm going to represent the derivative with respect to time in this course with dot. So that would be theta double dot, because it's the second derivative. If it was its first derivative, I'll just put angular velocity would have been just theta dot. So I'll put it here. Theta double dot. We can simplify this. Just get rid of one L from both sides, M from this side and the other side. So I'll move things around. You're going to get L theta double dot plus G sine theta is equal to 0. That's it. That is the equation of motion for this pendulum. Like a simple pendulum swinging around the point and the distance between the pendulum, the mass of the pendulum, and that point is L. Now, if you look at this equation of motion is pretty much a second order differential equation, right? We have the second derivative with respect to time, and consider the variable, the dependent variable is theta, right? Because we have the derivative with respect to time of theta. So this here is a second order differential equation. Now, it is a second order differential equation, but at the same time, it's nonlinear. If you remember from differential equation, this course is pretty much a combination of dynamics and differential equations. If you remember from differential equations, like the course, or the materials occur in that course, this is a nonlinear equation because we have a sine function, right? It's L theta double dot plus G sine theta. That sine makes this a nonlinear differential equation. And we actually did not cover, or we did not learn in differential equation how to solve a nonlinear differential equation. We know how to solve it numerically from a different course. I'm guessing you learned, maybe numerical analysis. But analytically, we actually did not learn that. So this is a second order nonlinear differential equation. So what do? We can't just stop here, right? This is just dynamics. We said vibrations is about finding the relationship. Here we are just finding the relationship between force, whatever the gravity is, and the acceleration, which is theta double dot or alpha. Now what we want to do is we want to solve this differential equation to find out what is the displacement, what is the angular displacement at any given moment. That's the part related to vibration. Right? We want to know where this pendulum is at any given moment by solving this differential equation. So I'll do a trick, right? To be able to move forward. I'll linearize this equation. How do I do that? Well, which part is making this differential equation nonlinear? Sine function. So I want to try to get rid of that sine function, sine theta there. How do I do it? Now, if I make a simple assumption that for small values of theta, I just want to study the system for small values of theta. That's the fundamental assumption I'm going to make. Right? The theta, the angle with which this pendulum is deviated from the equilibrium point, which is at the center, is a very small angle. I'm not going all the way to one side. Right? The angle is small, somewhere here. Right? As long as this assumption is true, or if we make sure this assumption is there, we can actually linearize this equation and solve this differential equation. Now, what happens if theta is small? I'm going to take you to old knowledge. I'm going to draw a unit circle here. If you remember unit circle, we were currently using these unit circles to study, to find sine and cosine values. Let me just draw it here. So this is a unit circle. What was a unit circle? Well, unit circle is a circle that its radius is 1. And so R is 1 here. Let me draw it here. So R, this is unit circle, meaning that R is equal to 1. And then it's this unit circle, this is cosine theta. This is sine theta. And for an angle theta, let me just draw it here. For an angle theta. If you remember, we were using unit circle to actually take a look at the values of sine and cosine. So if this is the angle theta, whatever is the projection or the length of this side is on cosine axis is the cosine value for this theta, and this is the sine value for theta. So that would be cosine theta, this would be sine theta. Now, let's see what happens. We use this as a graphical representation for sine and cosine. I'm hoping this is familiar to you. You have seen unit circle before and how it works. Let's see what happens when theta is very small. Right? For very small theta, let's see what happens. If I draw this again here. Now, I have a very small theta. What happens is that, well, this is cosine, and this is sine axis. Right? These represent the values for sine and cosine. If theta is very small, I'm going to draw it like this. Or maybe I can do better. Just a little bigger, but you can still do it as a small, so I can have some space. This arc here is r theta, right? The radius times angle in radians. Now r is 1, so this arc is theta. Again, this is sine theta, this is cosine theta. So for very small theta, I want you to look at this. This is the assumption that we're going to make over and over for the rest of the semester. Whenever I tell you small rotation, just use this, the result of this procedure. I'll show you what the result is. So when theta is very small, look at these two. This is the sine theta, and this is theta. So this is a curve here, but this is a straight line. Now, if this is very small, this line is very close, right, to this cosine or horizontal axis. Well, we can say this straight line and this arc are very close in terms of magnitude. Think about them this way. If we have this straight line, right, and this curve. Let me do a better job. I'll try to do a better job. And we have this curve. Like the longer, the larger this curve is, the more is the difference between this, the length of this curve and the length of the straight line. But for very small ones, you know, we can almost say this arc and this length are equal. And that's the basics. Basic for, or the base for this is this simplification or linearization. So for very small theta, I can say sine theta is almost equal to theta, right? Because if it's too small, then the length of the arc and the value of sine theta are going to be the same. Now, if you look at the other axis, right, the cosine axis. For very small theta, this line here, right, this line there, it gets very close to the horizontal line. Right? The angle is very small to 0. Theta is very small to 0 in this case. We're talking about a small angle. So what happens is that we can make this assumption that cosine theta is 1. Because cosine theta becomes very close to cosine 0, right? When the angle is very small. This line gets close to the horizontal axis. And what is horizontal axis? Here is 0, theta 0. So cosine 0 is 1. So always for the rest of the semester, this holds true for assumptions for small angle rotation. Assumptions for small angle rotation. Keep in mind, this means that this pendulum does not go far away from the equilibrium point. It gets close. And the approximate value for that, it's about less than 10 degrees. As long as your angle theta is less than 10 degrees, you are pretty fine. Bigger than that, well, you still can use this linearized equation that we're going to derive, but you are going to have a discrepancy between the theory and what you get in actual motion. So let's use this assumption. Well, cosine theta is equal to 1 is not the assumption I'm going to use here because I don't have any cosine, but I have sine theta. So replacing this in the second order nonlinear differential equation we got, this becomes L theta double dot plus G theta is equal to 0. And now this is something we can solve. This is a differential equation we have seen before. This is a second order linear differential equation. Let me put here linearize. We linearize this equation, right? From, let me point at number 1, and number 1 is linearized. It gives us this equation. This is the linearized version of the equation of motion for a pendulum, a simple pendulum. Now, I'm going to define two concepts before I start looking into how to solve this differential equation. I'm going to define two important concepts. These two are natural frequency and time period. I'm going to rewrite this equation first. I'm going to just define this both sides with L. So this becomes theta double dot plus G over L theta is equal to 0. This is the equation that eventually I get. Now, these two concepts I'm going to define again. Keep in mind, very important. We're going to use them over and over, no matter what the vibrating system is. We started from the simplest vibrating system, which is a simple pendulum, to introduce these concepts and see how the whole procedure works. So, what are these concepts? The first one, let me put here, I define these two concepts. Right. The first one is natural frequency. Natural frequency. So what is natural frequency? Natural frequency is the frequency, so official, I guess the formal definition is that, is the frequency, let's put it this way, if a vibrating system is disturbed, initially disturbed, and is left to oscillate on its own, so again, if a vibrating system is initially disturbed and left to oscillate on its own, the frequency with which it oscillates without external forces, without any external forces, is its natural frequency. So if I disturb this system, what do I mean by disturb? It means I just give it some initial displacement or some initial velocity, right? I can just give it some initial velocity, hit it. So either it's disturbed by some initial velocity or by some initial displacement. It's moved from its equilibrium point. And I just let it oscillate with no external force, right? So after I let it go or after I give it some initial velocity, I don't do anything to it anymore. I don't apply any more force to it. Right? I just let it oscillate on its own. The frequency with which it oscillates is natural frequency. So let me put it here. If a system, let's see, if a system is initially disturbed and left to vibrate or oscillate on its own without external forces, right? The frequency with which it oscillates or it vibrates is its natural frequency. So this is natural frequency, but what is the unit for this, and what does it even mean when I say the frequency with which it oscillates? If you look at the units for natural frequency, it might make more sense. So the units for these, let me put it here. Possible units you're going to deal with when you're going to see when you're dealing with natural frequency, or the general frequency, I guess. The unit can be radian per second or hertz. What is hertz? Hertz is basically just 1/2. Now, if we represent natural frequency with the unit radian per second, right, we call this circular natural frequency. And we represent that with omega n. Omega n, circular natural frequency. If we represent it with the unit hertz, we use Fn, and we just call it natural frequency. Now, think about the units. What do they tell us about natural frequency, or about frequencies as a general concept? You can think of frequency as a kind of velocity, right? Unit says radian per second. Remember, the unit for velocity was meter per second, right? How fast we go on a line. Now, radian per second tells us how many radians this pendulum is going to move in a second. Right? Radian is just the unit we measure the angle. Right? So let's, if it's easier to think about the degree. How many degrees, like how much of an angle this pendulum swipes in a second? Right? Depending on how fast, the faster it goes, the higher this natural frequency. Right? We'll see what does that depend on. Hertz is 1/2. What does that mean? It means number of cycles per second. That also shows how fast this pendulum swings. It says number of cycles per second. It means during 1 second of measurement, I want to know how many cycles. Do you remember I said cycle is when this one goes from one side to the other and comes back to where it was. And this is one cycle. Now, how many of these cycles this is going to complete in 1 second? That's the concept of hertz. So the faster this oscillates, the higher the value of natural frequency in hertz. The higher the value of natural frequency in radian per second. Now, for the rest of the semester, we are going to use the name natural frequency for both. So I'm not going to tell you this is circular natural frequency, this is natural frequency. We just identify or differentiate these two based on the units. So you look at the unit, it was like, oh, this is natural frequency in hertz. Look at the unit, this is natural frequency in radian per second. Okay. How do they relate? Well, that is very important. If you're given one, how can you find it? How can you find the value in the other unit? Look at this. This is radian per second. This is 1/2. So all I need to do is to multiply this Fn by 2 pi. So omega n, natural frequency in radian per second, is 2 pi Fn. Natural frequency in hertz. That's pretty much it. So if you're given one of them, we can find the other one. And this is a general equation, relationship. Even if it's just frequency, not natural frequency, you still can go from one unit to another, right? 2 pi multiplied by that, by hertz. Now, so does that make sense now what the concept of natural frequency is? Okay. Hopefully you're not sleeping and or half asleep, and actually you followed, so we're good. Okay, thank you, Cindy. As I said before, this is a remote course, so I actually don't see you guys. I need some feedback once in a while. Okay, so second concept is a little more familiar. The second concept is time period, which I already mentioned what it is. Time period. So time period is the time that takes for a vibrating system to complete one cycle. We represent time period with T, just uppercase T. As I said, just the time to finish one cycle. Now, how do they relate? These two concepts also are related. Look at the time period. Time period is time, so the unit is second. And look at the natural frequency. Like in hertz, it's basically just 1 over second. So you can easily see there is a relationship, right? Time period is 1 over frequency. Just you can look at the units and it makes sense. And also, if we just replace this 1 or F, 1 over T into the equation we got in the relationship we got between radian per second and hertz for natural frequency in different units, you can also write it this way. Omega n is equal to 2 pi over T. So for the rest of this course, these two concepts, we're going to deal with them a lot. That's how you go from one to another, and that's how we can change the units for natural frequency, go from one to another. Any type of frequency that you get. If it's in one unit, you can just change it to the other unit system. Okay, so good. I defined these two. Now let's go back to what we were doing. Let's go back to the equation of motion we got. Second order linear differential equation. And I said theta double dot plus g over L theta is equal to 0. This is the equation of motion for a pendulum. Now, if you replace, now for a pendulum, for a simple pendulum, omega n is square root of g over L. Whatever is the coefficient of the displacement, or theta in this case. So if use that and write the equation of motion, this becomes theta double dot plus omega n squared theta is equal to 0. Sometimes we use this form of equation of motion. When we're given the equation of motion, we can just find what is the coefficient of theta as long as the coefficient of theta double dot is, and that coefficient is squared of natural frequency for that pendulum or system moving in a rotational direction. Now let's talk about the equation of motion. So these two concepts are introduced. Let's figure out how can we actually solve that equation of motion. As I said before, we are in vibration, it's mechanical vibrations course, not dynamics. We could find that equation of motion before from dynamics. What we want to do is that we want to find out how can we solve this. Now, how do we solve a differential equation? If you have noticed from the course differential equation, I would say we don't actually solve differential equations. If you remember, the whole idea was, well, if this is a differential equation in this form, that is the solution, general form of the solution. If the differential equation is a different form, you were given a different general form of a solution with a bunch of constants, and you just had to find those constants from initial conditions or boundary conditions. So we actually don't solve the differential equation from scratch. We just propose a general form of a solution depending on the form of the differential equation. And then we apply boundary conditions or initial conditions to find those constants. Now, for this differential equation, right, the differential equation we had, the L theta double dot plus G theta is equal to 0. I want to solve this, right? It's a second order differential equation. I propose a solution in this form. I say theta, which is a function of time, it's a sine omega n t plus phi. It's a general form of the solution. And a and phi are just constants I have to find from in the initial condition. Now, why did I propose this? Well, you know what? Actually, that's not the only solution. You might propose a different solution. The idea of using a sine or cosine function, because I know this is a motion that goes, it follows the same procedure, same path, goes back and forth, back and forth. So what does that remind me? It reminds me of a sine function. Right? I can imagine that it's going up, down, up, down. It repeats one type of motion. So I thought, well, why not just propose a solution in general form that is a sine function? So I'm using that idea. Now you might say, well, it is, if it's a repeating motion, why not using a cosine function? Why not just say a cosine omega n t plus phi? That actually works. Why don't I just use an exponential function? You can actually use an exponential function and just take the real part as the solution. That works too. So again, as I said, this is differential equation we're trying to solve. We just propose a general solution. I propose this. You might propose something else. As long as the proposed solution, the solution you propose, you can find the constants using initial conditions for the system, that can be a solution too. But for the sake of uniformity in vibrations, we just go with this general form of solution. So we have two constants, A and phi are constants, A and phi, constants, unknown constants. So we need two initial conditions to find these two constants. What are those initial conditions? Well, I put initial conditions here. Look at the pendulum. What possible initial conditions could I have? There are two possibilities. I can take this pendulum all the way to some point and let it go. So whatever is the initial theta that I have is an initial condition, depending on where it starts its motion. So I'll say, well, one initial condition is what is the value of theta, the deviation from equilibrium point, at t equals to 0. And I'll just represent that with theta naught, the initial displacement. The second possibility, in the second initial condition, is how fast I let it go. I push it. I can let it go, take it here and let it go, or I can take it here and push it. So I can give it some initial velocity, which means a second type of initial condition, which is theta dot. Right? As I said, theta dot is just the derivative of theta with respect to time, just angular velocity. And I'll represent that with theta dot naught. So now I have a differential equation. I propose the general form of the solution, and I have initial conditions. I can use these initial conditions to find those two constants that are unknown at the moment. How do I do that? Well, I'll just easily plug them in. If you plug these in, you'll get, well, for if you put t as 0, so you'll get theta naught is equal to, just put t as 0 here. It becomes a sine phi. This is the first equation. Now take derivative with respect to time, right? Theta dot t. What is the derivative of this with respect to time? Right? Sine, well, phi is constant. Omega nt, whatever is derivative inside this, was going to be omega n, comes out. So I'll have a omega n, sine becomes cosine. Cosine omega nt plus phi. That would be theta dot. Theta dot is not something I proposed. It's just the derivative of the proposed solution, general form of the solution. So now if I plug in t equals to 0, this becomes theta dot naught, which is what I used to represent the initial velocity given to the system. Well, plug in t equals to 0 to theta dot t equation. This becomes a omega n cosine phi. Now I have two equations, two unknowns. I'm looking for a and phi. How can I find them? I'm going to use a little bit of tricks to solve and find out what these values are. First thing I can do, if you look at these two, I can actually divide these two equations. What do I do that? Doing that, I can get rid of a. It's one of the unknowns. Right? If I just divide the first one and the second one, so if I divide theta naught over theta naught dot, what do I get? I get 1 over omega n, and sine over cosine becomes tangent, tan phi. See, now a is out. I only have one unknown, which is phi. So I can actually find it from here. Phi becomes tan inverse, right? Theta naught omega n, theta naught dot. It's important. So this is this is the equation to find the constant phi from those two initial conditions I had. How do I find a? Now, you can actually find a too by just moving this omega n to the left side, this one, you can move it here and square both sides. So here's what I'll do. If I square both sides, it's going to be theta naught squared plus theta naught dot over omega n squared, and I square the other sides and sum them up. It's going to be a squared, I factor it out, sine squared phi plus cosine phi squared. Let me see where am I going. Sine squared plus cosine squared is 1. So what I get from here is a. I can actually find the value of a. A becomes the square root of, if I move things around, this would be theta naught squared omega n squared plus theta naught dot squared. Let me just keep this square root on the numerator, divided by omega n. That becomes the value of a. So I propose the general form of solution with constants. I use the initial conditions to solve that, to find those constants in the general form of the solution, a and phi. And now I have the capability to find these two constants as long as I can calculate, as long as I have three things. As long as I have the initial velocity, how fast I'm pushing or pulling this. Initial displacement, where am I letting this go? Is it here, here, or here? And I know that as long as I know the natural frequency, keep in mind natural frequency was here. This is the natural frequency. Meaning that all I need is to find the length of this string. So now you see why, let me just mention one more thing before. So here, phi, we call it phase, and a, we call it amplitude. So if I put this back to the general form of the equation, theta t would be A, which is square root of theta naught squared omega n squared plus theta naught dot squared over omega n, right, sine omega n t plus, what is phi? Tan inverse theta naught omega n over theta naught dot. So this would be the final, we call it system response. What do we mean by system response? It means that system response. It means that how does that vibrating system, in this case a pendulum, respond to given to a given initial given set of initial conditions, to a given initial displacement and initial velocity. How does that respond? How does that move? This tells me where this pendulum is at any given moment, right, during the motion. If I let it go from here, after 2 seconds, where the pendulum is. Is it here? Is it here? Is it there? Is it at equilibrium point? That's what it tells me. So now it's not just about the equation of motion. Now I have the response of the system to some given initial conditions. One more thing I wanted to just refer to here, mention, is that look at the equation for simple pendulum natural frequency. This is the natural frequency. It's the square root of G over L. The only parameter that we have there that is related to the system is the length of the string. So when Galileo was looking at those chandeliers and he realized that no matter how heavy they are, or no matter how strong the wind blowing and moving them is, they still have the same natural frequency. They had the same natural frequency, or in his case, same time period, because you can find time period here, right? From there, you can also find time period. T would be 2 pi over omega n. So as long as omega n is, omega n depends only on the length of the string for this pendulum, time period depends on that too. So it doesn't matter how heavy this mass is or how hard I push this. If you actually make the measurement, the time that it takes to finish one cycle is the same as long as I just don't change the length of the string. And you see, mathematically, we see exactly what Galileo saw when he was looking at those chandeliers. Okay. Any question up to here, folks? Did it make sense? Where did we start? We started from the pendulum. We draw the free body diagram and kinetic diagram. We wrote down the equation of motion. It was a second order nonlinear differential equation. So I linearized that with the explanation I gave you about what happens when theta is small. So that's the very big assumption we have to keep in mind. When theta is small, I can linearize this, and then I define two concepts, natural frequency and time period, went back to my equation of motion, and I solved that equation of motion, which is now a second order linear differential equation from what we knew from differential equation. I suggested a solution with constants, used the initial conditions, and found a system response. Are we good up to here? Good? No good? Give me some. I don't actually have your videos on, so I am not sure if you guys are following or you're good.
Dr. Masood, I have a quick question.
Sure, go ahead.
I'm a bit confused on where that equation came from, the theta, like the A sign.
This one here.
No, to the left.
To the
Like the
left,
one, like before the initial conditions.
before the initial condition. Oh, this one.
Yeah, that one.
Okay, so this is what I said. This is not this is a suggested solution. I suggested that solution. I said, well, I know that this system is oscillating in the special form. It's oscillating like this. And I said, I know this differential equation. I just suggested that solution. I said, this is a general form of the solution, the way we solve differential equation. I said, if this is the differential equation we are supposed to solve, this one, right? This would be the suggested solution. We don't need to know this. It doesn't come from any solid math, right? I just said this is the general form of the solution. And I say it is with two constants, and I prove to you it is because I can find these constants from initial conditions. Now, you might tell me, no, I think it might be a different function. It's all good. Just use a different function. And as long as you can find the constants in that function using the initial conditions, that also is a solution. Right? But as I said, for the sake of uniformity, we just go with this. It could be a cosine function. It could be a sine function with a different combination for it's the argument of sine function, like inside this parentheses. Does that make sense what I'm saying?
Yes, that makes perfect sense now.
Okay.
Right. Thank you.
Of course. Okay, so some reason I erased this. Let me just write it again. Now, this is a kind of long system response. It doesn't really tell us that much about what is going on in this system. So you will see this habit, this thing that we're going to do over and over in this course, that we love plots. We love to look at graphs instead of equations, because graphs can talk, as I say. You understand them way better than equations. This is a long equation, doesn't really give me that much. But if I plot this, I already put together a general plot so I can do things on top of it. There you go. Now, if I plot this function, the system response, this is what we're going to get. This would be theta t, and this would be the axis time, second. Theta t is radians. Now, let's look at this. This is going to give us a lot of things from the equation. The time, first to start with here, this is where the pendulum is at the beginning of the motion. What does that mean? So what is this value? What is that at the beginning of the motion? That's nothing but theta naught, right? The initial displacement. Whatever this pendulum is, at t equals to 0, that's theta naught. What is the maximum value on this plot? Right, the peaks here, here, and next one. What is this maximum value? Looking at the equation, going back here, we have A sine omega and t plus phi. Look at the suggested solution. What is the maximum
so the
value?
maximum value would be the amplitude?
Yeah, that would be A, right? Exactly. So one is correct. One would be the maximum value for sine function. So theta t is maximum when that sine function is maximum.
And then when it reaches the next amplitude, that'll be the phase?
Say it again.
When in between the two amplitudes, that would be the phase?
On the plot, you mean?
Yeah.
You're talking about from here to here?
Correct.
I'll talk about it in a second.
Okay.
But let's just figure this out. Right? Let's see what this is. This is, well, the plot is showing, the plot is A sine omega n t plus phi. Right? Now sine is changing from -1 and 1. It's a trigonometric function. The maximum value you can get for sine is 1. Meaning that the maximum value of this motion would be A. Does that make sense? Okay. Now, what else we have on this plot? We can find, I forgot, I actually can't see who is asking, but I can make a guess. Was it Dominic or Yusuf? Or was totally wrong?
No, it was Dominic.
Dominic, yeah. So, not bad. So this distance between these two peaks, this is an important value. This is actually our time period. Think about it. When we are all the way on one side, we are as far away from the equilibrium point as possible, which is maximum A. Right? So here, this point is when I am at the maximum deviation from equilibrium point. No, this pendulum goes all the way to the other side. When it's all the way to the other side, I'm here. Like this point, all the way to -1. This is all the way to the other side. And comes back to where it was, all the way to this side. So I go back here. So from this point to this point, let me erase the other one. From this point to this point is one cycle, which means the time that it takes from that point to that point is time period. So we define time period as the time that it takes to complete one cycle. Right? So T, basically this is the value of time period. So it's going to be 2 pi over omega n. Right? Or you can just put it as 1 over Fn. So that's the value of time period. What else I can get? Now this is the plot for theta, angular displacement. Right? What is the slope of this? The slope of this is the derivative with respect to time, right? Because this is theta, so the slope of this would be d theta dt, which means that the value here, the slope of the line here, this value is theta dot naught, the initial velocity. How fast I push this at the beginning of the motion. So on this plot, we can see where the initial displacement is. We can see where the initial velocity is, the slope of the line at the beginning of the motion. We can see where the maximum amplitude is. We can measure the time period from this plot, as long as we find the distance between two peaks. And keep in mind, time period can also be the distance between these two. Can also be the distance between these two, as long as you finish a cycle. You can consider the beginning of a cycle at any point. So if I think about these two as time period, meaning that I'm measuring one cycle from the equilibrium point, goes to the other side, goes back, come where it was. It's less obvious compared to measuring the time period or one cycle for the whole motion, but it's still the same thing. Now, one more thing on this period. What are these points? This point and this point. What do they represent? When does this happen? When do we pass this point? This point, this point, or this point? These are the points when we pass the equilibrium point, right? This is theta equals to 0. These points are theta equals to 0. Look at the y-axis, meaning that we are passing the equilibrium point. Swinging as passing the equilibrium point. That point is one of those points, goes back and forth, keeps passing that point. Meaning that that's where we have the maximum velocity. Right? You're going all the way from one side. If you remember potential energy and kinetic energy, we have the maximum potential energy when we're at the lowest position. Meaning that we have the highest velocity. So these are the maximum velocity. This is theta max. Theta dot max, sorry, maximum angular velocity for the system, right? And there is one more thing that physically it makes less sense, but if you're looking for phi, as Dominic said on this graph, you can just extend this, and this distance here gives you phi n over omega n. Sorry, phi over omega n. I don't know where I get phi n. Phi over omega n. Initial, like the phase for this motion. It's more like about the signal, meaning that that's how far we are from theta equals to 0. And if you divide that, it makes sense that the unit phi is an angle, so it's a radian, and omega is radian per second, so that gives you a second, meaning that that's the amount of time that you are away from the equilibrium point when you start your motion. Okay, so I think it's pretty much everything on this. Now, a couple of things keep in mind, because I'm going to post the homework solution for this, and it's pretty much just a pendulum to find the solutions. Now, things that I can ask you, right, when I give you this plot or when I ask you to look at a pendulum. Right? If you are given the length of the pendulum, here, if you're given the length of the pendulum, we can find the natural frequency. If you know the natural frequency of the pendulum, we can find its time period. If you know the time period, and if I give you initial conditions, right, meaning that I give you how fast the initial velocity is and how far we are from the equilibrium point, right? Using that, and knowing the length of the pendulum, which you use to find natural frequency and time period, you can find phase, you can find amplitude, and from there you can find system response. Right? Just need to know what are the initial conditions and the length of the pendulum. So now,
we can apply the same concept to a spring mass system, correct?
Sorry, say it again.
We can apply the same concept to a spring mass system since it's going to be in the same kind of sine wave.
Exactly. So that's the topic for the next thing that I'm going to talk about. I'm going to talk about spring mass system, and you'll see how exactly the same thing we are going to face. Right? The other thing is, keep in mind theta is always in radian in these calculations. You can convert it to degree at the end, but whenever you want to plot an angle, theta or phi, sorry, plug in a value for an angle, theta or phi, always in radians, nothing in degree. At the end, you can convert it into degree. For calculations, always in radians. And let me see if there's anything else I want you to pay attention to. Last thing that is important, when I tell you that I let this pendulum go, I'm actually giving you one of the initial conditions. And that initial condition is initial velocity. When I let a pendulum go, means I don't give it any initial velocity. It means initial velocity is 0. So if I tell you I let this pendulum go at the angle of 5 degrees, first, remember the angle should be in radians, should convert that. Second, when I say let it go, it means I gave you the second initial condition, meaning that initial velocity is 0. So keep these two in mind. Okay, I have 10 minutes. I just want to talk briefly about the springs. You already know springs. You know what they are, the forces in the springs. So I'm going to be brief on this. If I just talk about the spring today, then we can talk about the spring mass system in next class. Now, what is a spring? I do have one here. This is spring. Now, spring, I don't know how to define this, but we can just basically simply put a few comments. It's a mechanical link Right? We use that to connect things together. The second thing about the spring is that typically we consider that as massless. So we typically in this course ignore the effect of mass of the spring. Right. If you want to take it into account, if I ask you to take it into account, which in one of the projects I'll ask you, I'm going to ask you that if we want to take that into account, we just add 1/3 of the mass of its mass to the total mass of the system. So what I'm trying to say is that if I have a series of mass attached to a spring, like this, you can see it's an oscillating system. Talk about it more. I typically consider this spring as massless. But if I tell you that the mass of the spring is 50 grams and I want you to consider that, 1/3 of that mass you should add to the general mass of the system. That's the idea. But unless I tell you, you can always safely ignore the mass of the spring. Now, how does where do we see springs? Typically, we see it in you've seen it in retrievable pens and pencils. You've seen it in, like, I guess, typical things around you, like staples. Right? They have a spring to push things back to where they are. We see them obviously in suspension systems for cars, and we'll talk about it more. And in a spring, again, just a review, the force is related to the deflection of the spring. So the further we deflect this spring, this spring is a kind of tension spring, but if it's type of spring that you can push and pull, even if you push and you want to compress it, it's going to apply a force. So there's always a relationship between force and deflection. Right? So they are related. How are they related? Well, the way they are related tells us about what kind of spring we're dealing with. Right? So if the relationship is linear, so we have a linear spring, which is pretty much the type of a spring, the only type of a spring we're going to cover in this course. Now, if the relationship is nonlinear, we have a nonlinear spring. Now, let me just plot this. Let's look at this, the relationship between force and deflection. I'm going to call this deflection, let's S, and call the force F. Now, if the relationship between the force and deflection is linear, meaning that if we plot that relationship, that's pretty much just a linear line, straight line. And the slope of this line here is, we represent that with K, which is, K is spring stiffness. And these are not new concepts. Hopefully you've seen this in dynamics and before. So we can say F is equal to KS, depending on how strong this spring is. This slope can be higher. Now, what if the relationship is not linear? What if we have a relationship like this? Let me plot it this way. What if we have a relationship like this? What does this tell us? It tells us after some certain point, right, when the spring is stretched, the left side, the negative side, is talking about the compression spring. So in this case, I only have a spring that goes under tension. So I'll just talk about what happens on the right side. It's the same thing about the left side on the S axis. Now, this dotted line tells me that behavior in the spring, if I measure the amount of deflection in the spring and how much force I apply to it, it tells me that after some amount of deflection, it becomes easier to stretch the spring, meaning that I need less force to stretch the spring after I pass some initial deflection. So this is more like a soft spring. Like this is nonlinear. Let me use the same color. This is nonlinear, and it's a soft spring. And if I want to write the equation for this, this would be F is equal to, I think we can use K1S minus K2S, that should be K2. K2S to 3. So that shows the relationship between the force and the deflection. The farther we get from the equilibrium point or the zero tension or deflection, the easier it gets to stretch the spring. The opposite is true too. If I have this type of a spring, this is also a nonlinear spring, but it's hard spring. If I want to show the relationship between force and spring stiffness, now we have two values for spring stiffness, obviously, like the other nonlinear. We have K1 and K2. K1S plus K2S to 3. Right? This is a third order line. This tells us that it gets harder and harder to deflect the spring the more I deflect it, I guess. So look at the red line. It says I need more force to stretch the spring for the same amount, like after I get away from the initial non-stretched length. Does that make sense to you, folks? In this course, we're just going to focus on linear spring, and all the springs we're going to have are going to be F equals to Kx or Ks. I'll replace S with X later on during the course. It's more convenient. But that's the relationship we're going to deal with. Let me change it to green. So that's the type of a spring we're going to do. Stiffness, spring stiffness. I'll talk about how can we measure it actually in using experiments, but that's pretty much it. Any question, guys? End of the class. So do you have any question about what we covered? I'll talk about spring mass system in next class, but I just wanted to review what the spring is, and you already know that. Any question? No question at all.